In this video, we're going to take a look at molecular bonding, bonding theories, and molecular geometry. So just like atoms have atomic orbitals, molecules have molecular orbitals. They're all the orbitals that belong to a molecule, whether they're bonded or unbonded. But when two atoms come together to make a bond and share their electrons, they overlap their atomic orbitals and they make what we call, again, these molecular orbitals. And in this case, that molecular orbital is called a bonding orbital because they're sharing two electrons between them. So there's different ways in which these atoms come together and form bonds. The first way is what we call a sigma bond. Two atoms are going to come together and overlap their atomic orbitals along the bonding axis, creating this new molecular orbital that is symmetrical around the axis between the nuclei of those two different atoms. That is a really good strong attraction, again, because we have the protons in the center of each of those electrons directly between them. We do get that positive, negative, positive, opposite attraction like we've discussed before, holding it together, and it's a really strong bond. And here we see those p orbitals overlapping. It also could be s orbitals that overlap, but in this case p orbitals overlapping on the bonding axis, again creating that symmetrical now molecular orbital along that bonding axis. We're going to share those electrons. And we notice also that orbital is larger in the middle because that's the most likely place to find those electrons, is directly between those two atomic nuclei of those two different atoms that are sharing those electrons. There's a little bit that could still be on either side because, again, it's a mathematical probability of where those electrons are, and the most likely place to find them is going to be directly between. And again, those sigma bonds are always the first ones that will form. And then if you need to make a second bond, we make what we call a pi bond, or also if you're making a third bond, we make a pi bond, because electrons can't exist together in that same small space. I can't put a second pair directly between those two atoms. So what happens is these two different atoms take their p orbitals, they stand them up side by side, and they overlap above and below the bonding axis, creating two little blob areas where the electrons are going to be that are not symmetrical about that axis. But again, they can't go directly between those two atoms again because they'd be repelling and it would not work out too well. And relative to that of the sigma bond, the pi bonds are weaker, but a molecule that would have a sigma bond with a pi bond would be more difficult to break apart. You have to break apart two bonds, but relative to that sigma bond, it is less energy to break it apart. So here we see those p orbitals that are side by side overlapping, again creating that bonding orbital above and below the axis. Again, there would be a sigma bond also there within the axis. If you overlap the two different diagrams, you would have, again, these two different molecular orbitals where they're sharing the electrons. But here, just these pi bonds, again, are the p orbitals side by side overlapping, creating an asymmetrical bonding axis orbital that they will share the electrons with. And because we know these electrons repel each other, they want to take up space, and that space that they want to take up is going to create different shapes, different geometry for these different molecules. And when we have just one central atom, we can predict what shape that molecule is going to be based upon the amount of electron pairs that are there. It's called the VSEPR theory, valence shell electron pair repulsion. Again, because electrons do not want to be near each other, they'll spread out as best they can to give themselves as much space, creating, again, these different shapes. Trick with these is, you got to remember though, these molecules living in 3 dimensions. When you draw them down on your paper and you write out your Lewis dot structure diagram for these, then they're going to look very different than what they actually look like in real life, because the way you would spread them out on the paper versus the way they're able to spread out in 3 dimensions makes it a little bit tricky. So we draw out these structures and we do our Lewis dot structures and we try and predict the geometry. It is both the bonded and unbonded pairs of electrons that count towards that shape. And even more so, the unbonded pairs actually make the bonded pairs get squished closer together, because when they're not being pulled on by another atom, then they're held a little bit closer to the nucleus of that atom and pushes, again, those bonded ones closer to each other, shrinking down those different angles. So those unbonded ones being held closer do, again, result in more repulsion because those electrons being closer to each other, needing more space. So here we see some common shapes based upon, again, the number of pairs of electrons that are around that central atom, and looking at how many are bonded, how many are unbonded. So the most common shape is going to be a tetrahedral shape, because if you have 4 bonded pairs, we know the octet rule, they like 4 pairs of electrons. If you have 4 bonded pairs of electrons, we see it has a tetrahedral shape. In the case of like methane, which we'll take a look at in a second. But if there's one unbonded pair, well, now it's trigonal pyramidal, like we see with ammonia, NH3, and then The last one we see in that tetrahedral column there, if we have two pairs of electrons that are bonded, two that are not bonded, that makes a bent shape. And again, that's like water, which hopefully you're pretty familiar with. Again, so even water having those two hydrogens bond to one oxygen, you think, oh, it'd be linear. That'd be the best way to spread them apart. But we have those two non-bonded pairs of electrons, which are pushing on those other ones. And again, actually even shrinking it down, as we're going to see now. These are these three different tetrahedral base geometries we see here. Again, we got methane to the left, we got ammonia in the middle, and water to the right. And in the methane, where it's tetrahedral, we have four all bonded pairs of electrons around that central atom, and they spread out again to the best of their ability. We see that the angle between those different carbon-hydrogen bonds is 109.5 degrees. But in ammonia, where it's NH3 and you have that one lone pair we see up top, well, now it pushes those bottom three bonded pairs together, and that angle drops down to 107. And then lastly, we see over there with water, two bonded pairs, two lone pairs, those two bonded pairs getting squished even a little bit more together, and now that angle is 104.5 degrees. So when you have two atoms coming together to bond, and they have these different s and p orbitals which are going to be overlapping the bond, and they have different energies, as we already know, well, what happens is they make these hybrid orbitals that make it easier for them to bond, give them a better ability to overlap, and also give less energy to make it easier for them to be able to overlap and bond, because they want to be able to bond to become stable, so they have an easier path to be able to bond if they have a better ability to overlap, and again, lower energy, because we like to have lower energy, it's less work. So hybridization actually we can use to then talk about that shape. Looking at the shape of those different molecules, we can look at the hybridization based upon how many overlapping orbitals they need. So again, starting with methane, we have all single bond hybridization. Then we have these four different pairs of electrons being formed. So we're going to take our s orbital and our three p orbitals, and we want to be able to fill those up again to make four pairs to have our octet. And so I'm going to make four different single bonds with four different hydrogens from that central atom of carbon. So we're going to take our 2s orbital and three of our 2p orbitals. We're going to kind of like throw them in a blender, mix them all up, and again make four new orbitals, which we're going to call sp3 orbitals that'll have the same amount of energy, because again that s and that p, we know p has slightly more energy than s, and then it's really difficult to figure out, well, which of these hydrogens is going to bond with the s and which ones are then going to have to bond with the p. So again, we mix them all together, we make these four new orbitals of equal energy, that is even lower in energy than those s and p's. That way they can make it easier to bond and come together and complete their octet. However, then when I have a double bond, again, to make a double bond, I need a pi bond. And that pi bond is going to use up one of those p orbitals. I'm only going to bond with now three different orbitals. So I have one pair already accounted for in that double bond with one of those pi bonds. So I'm going to make three different bonds to three different atoms with only three hybrid orbitals. So I'm going to take 1s and 2p orbitals. I'm going to mix them all up so that way now they can bond together and bond to three different atoms and make these three new hybrid orbitals called sp2 hybridization. Again, because I'm going to take that 1s with those two now p's that I'm going to use, because again, one of those p's is already accounted for with a pi bond, and make three new sp2 hybrid orbitals, which again will have less energy than those s and p's from which they came from, making them better to overlap, easier to overlap, and complete our octet. And the last kind of common one we're going to talk about is when we have like a triple bond. So now I'm going to need two pi bonds. I'm going to utilize two of those p orbitals. I'm going to bond to just now two different atoms. This also works out the same way if I have two double bonds, like in carbon dioxide, where carbon's bonded to two oxygens, each with a double bond. Same idea, where I'm going to have to only bond twice within the bonding axis, and therefore only have to make two different hybrid orbitals, or in this case we see HCN, again where carbon's going to be triple bonded to nitrogen and a single bond to hydrogen. So I'm going to take just one s and one p, because again two p's are already accounted for with pi bonds. I'm going to throw these in a blender again, mix them up, and make two new bonded hybrid orbitals to be able to overlap and share those electrons on the bonding axis. And now since it's made of 1s and 1p, we have two new sp orbitals, again of equal energy, lower than that of the s and p which we began with.